Welcome back, everyone, for the second part of this lecture of today, or fourth day of the school. Thanks, Aurora, and the space is yours.
Okay, great. So for the next part, we're going to be looking at how you can characterize exoplanets at high resolution. And I'm going to just start today with doing one of the methods. We're going to start with the Rossiter-McLaughlin method, and then we're going to finish up the rest of the methods tomorrow. Just the other method, we're going to be looking at transit and emission spectroscopy at high resolution tomorrow. Okay, so let me share my screen. Okay. Okay, so like I said, there are different ways that you can not only detect an exoplanet, but also characterize an exoplanet at high resolution, so with high resolution spectroscopy. And the first one that we'll talk about today is the Rossiter-McLaughlin method. And this is used to determine the spin-orbit alignment of the planet and the star. And so I'll go into more detail about that in a second. And then tomorrow we'll look at exoplanet transmission spectra at high resolution spectroscopy and exoplanet emission spectra. So the Rossiter-McLaughlin effect happens as the planet passes in front of the star. And because the star has some rotation velocity, like we saw for the star spots, you get the planet blocking certain parts of the star. And as the planet begins to transit, if we have a system that is aligned with the planet's orbit and the spin orbit axis aligned, then the planet will hide part of the star that is blue shifted. And so what this will look like in an absorption line, so here's our single absorption line, and the planet is blocking some of the blue light. And so when we would normally have this nice full absorption line, we now have part of the blue light being blocked by the planet. And then here, when the planet moves into the center, it's now blocking some of the light that is not redshifted or blue shifted. So the light in the center of the line. And then at the end of the orbit, the planet is blocking the redshifted light. And so on the redder side of the absorption line, you get less flux. And so if the star and the planet's rotation axes are aligned, you're always going to get this blue shift blocking to red shift blocking. But if we have different things, so say here, now we have the star's rotation axis and the exoplanet's orbit axis are not aligned anymore. So now we're going to get, at the beginning, the same thing where the star is now the exoplanet is blocking the blue shifted light at the beginning, but then in the middle, instead of blocking the center, it's going to still be blocking more of the blue shifted light. And at the end, instead of blocking the red shifted light, it's going to be blocking the light that is neither red shifted nor blue shifted. And so you're going to see something like this happen with the absorption lines. And so by modeling the absorption lines and the radial velocity shifts that we measure, we can actually figure out what part of the star the exoplanet is blocking. And then we can figure out how the rotation axis of the star and the orbital axis of the planet are aligned. And so what we can do to actually measure this is we can measure radial velocities of the star as the planet is transiting. And so when we talked about this earlier, let's see our radial velocity curve from earlier. Sorry. Okay. So this is the full radial velocity curve. Now, just to give you a bit of a time, we're only talking about a very, very small portion of the radial velocity curve as the planet is transiting. So maybe actually, which one has phase? Okay, this has phase. So when the planet is transiting, we're at phases of about minus 0.1 to plus 0.1. So we're talking about something on this very short time scale. So just remember that when we're thinking about the Rosner-McLaughlin effect. We're looking at something from minus 0.1 to 0.1 phase. Okay. Right, so here we're looking at hours, and in phase it's about minus 0.1 to 0.1. So on top of the long-term periodic trend, you're going to see this wiggle as the planet transits in front of the star. And so if we have this aligned situation and we have the planet blocking the blue light first, when we do a cross correlation, all of the lines are going to look like they're slightly red-shifted. So that's what we see here. At the beginning of the transit, all of the lines look like they're red-shifted, and so we measure a net positive radial velocity at the beginning. And then in the center of the transit at phase 0, we measure no radial velocity offset. But then at the second half of the transit, as the planet is blocking the red starlight, we actually are going to measure a slightly bluer radial velocity than we normally would. And so that's what we're seeing here. And by modeling this shape here of the radial velocity variations that we measure, we can tell how the planet is aligned. So in this case, we get a nice symmetric increase and decrease. If the planet is slightly misaligned, we still do get the planet blocking some of the blue light, but this increase here is just much smaller. And most of the time, the planet is blocking the red light. And so we see a much larger negative dip where we measure bluer radial velocities. And lastly, if the system is even more misaligned, we never get the planet blocking any of the blue light. So we always measure, we never get the planet blocking the blue light. It's always blocking the red light. And so we always measure a bit of a bluer line. So we get this only dip here.
Hi, Aurora, excuse me.
Mm-hmm.
You have a question in the chat. Could a considerable amount of dust affect the measure?
Yeah, so it depends on, I'm not sure exactly where the dust that you're talking about would be. So if you're looking maybe like at a young star that still has like a dusty disk, then you can get, effects of dust and gas from the disk. There shouldn't be too much dust in any more evolved exoplanet systems. You can also maybe like if the planet had rings or dusty rings, this would affect it, or something like that. So does that answer your question? If you had a more specific dust application, you can let me know. Okay, right. So this is kind of our cartoon of what it would look like. And here we have some actual data of different systems. So here we have the exoplanet system called HAT-P4. And all of these exoplanet systems are just named after the survey that discovered them. So we've been working with a lot of WASP data. That's one transiting survey. And then we also have HAT is a different survey. So all the exoplanets discovered by this HAT survey are called HAT-P4, HAT-P30, etc. Okay. So just like we saw before, if we see an equal amount of increase as we do decrease, we know that the exoplanet has to be well aligned with the star's spin axis. But if we see only a decrease, we know that the exoplanet has to be transiting mostly the red in front of the red shifted part of the star. And so this is also interesting. If we see, so normally we have this increase and then the decrease. But if we see the decrease first and then the increase, we know that the exoplanet has to be transiting in a retrograde orbit. So what that means is normally we have the star spinning in one direction, and we have the exoplanet orbiting in the same direction that the star is spinning. This is called a prograde orbit. But we can have retrograde orbits where the star is spinning in one direction and the exoplanet is orbiting in the opposite direction. And so that's what we see here is this retrograde orbit. So we've actually measured examples of retrograde orbits, completely misaligned orbits, and of course well-aligned orbits, which is a well-aligned orbit is what we expect. And the reason that we care about measuring these spin orbit alignments and misalignments is this can tell us a lot about exoplanet formation and evolution, because according to our models, all of the exoplanets should form in a disk. We have the star and it's rotating, and then we have this disk of gas and dust. And this should be rotating in the same direction as the star. If we kind of just think of the generic model. And so the exoplanets forming in this disk, you would think would be perpendicular. Their orbits would be perpendicular to the star's rotation, because that is how they would form. And then it should be moving in the same prograde orbit. But when we see things like misaligned orbits and retrograde orbits, we either have to we have to think about what happened in order to make the exoplanet in a misaligned orbit. Maybe did the disks become misaligned at some point during the formation, or does this happen after the formation, and maybe there's interactions between multiple exoplanets which cause one exoplanet to be completely ejected from the system and another one to have a weird misaligned orbit. So maybe dynamical interactions between multiple exoplanets cause this. Or maybe the disk itself can be moving and the disk is not always aligned with the orbit of the stellar rotation axis. And so by seeing how many planets and what type of planets have well-aligned orbits and misaligned orbits, we can learn a lot about the formation and evolution of these systems. And in order to measure this, you can see here that we need to measure 20 meter per second precision in order to measure kind of these orbits. And so the meter per second precision is something that you need really high resolution spectra to do. Okay. So that's the end of what I wanted to talk about today. So let me know if you have any questions. And next we'll be moving on to the Kahoot quiz.
Hi, Aurora. No, so far there are no more questions on the chat.
Okay, so I'll just move on to the Kahoot quiz. And if you have questions that arise during the Kahoot quiz, then we'll come back and we can do more questions later. Okay. So I will share the Kahoot screen. So the game pin is 8286164. Okay, so I'll just wait 1 more minute. Okay, there's 14 people on, so I will start. Oh, good, I waited another minute and somebody else came on. Okay, so I'll start now. So the first question is, which will result in the largest radial velocity signal of the host star? A 1 Jupiter mass planet at 1 AU, a 1 Earth mass planet at 1 AU, a 1 Jupiter mass planet at 0.05 AU, or a 1 Earth mass planet at 0.05 AU. Okay, nice job. So a lot of you got this. The larger or more massive the planet is, and the closer to the star, the larger the radial velocity shift on the star is going to be. So the easiest ones to detect are large planets at close distances. Okay, so next, what properties can you infer from a radial velocity detection of an exoplanet? Can you get its radius? Can you get its mass? Can you get the mass times the sine of the inclination, or can you get all of the above? Yes. So you definitely cannot get the radius from a radial velocity detection. The mass you can get sometimes if you know the inclination, but the best answer that you'll always be able to get from radial velocity detections is the mass times the sine of the inclination. Because this is using the center of mass, it doesn't matter how large a planet is. It's just the mass of the planet that's causing this wobble of the host star. Okay, true or false? The radial velocity technique can discover planet systems at every inclination. Okay, great. Most of you got that false. So the radial velocity technique can only discover systems where the planet is moving in the line of sight, in our line of sight. So if you have a face on orbit, we're never going to be able to discover that planet with radial velocity. True or false? You will measure larger radial velocity shifts due to a planet around a low mass star than a sun-like star. Oh, I'm sorry. I didn't increase the time on this one. Okay. Sorry about that. I will wait a second for the YouTube to catch up, and then I'll just explain the answer. Yeah, so the lower mass the star, the larger the radial velocity shift is going to be. And so that's why we're looking around a lot of low mass stars in order to detect Earth-like planets, because the center of mass will be farther away from a lower mass star than it is for a sun-like star. At phase 0, the exoplanet is behind the host star. Oh, again, I'm so sorry, I forgot to change some of the times, it looks like. Okay. Again, I'll just explain the answer and then wait a little bit. Yeah, so at phase 0, the exoplanet is in front of the host star. This is when the planet it's transiting is at phase 0. So good job for those of you who got the answer in on time. And again, I'm sorry. Okay, hopefully I didn't do that on any more. What are the benefits of using cross-correlation to measure radial velocities? Oh, good, this one's longer. Information from many spectral lines is combined. Weak signals can be more easily detected. Noise in the spectrum does not significantly affect the detection, or all of the above. Okay, great. Most people got this. Yeah, all of the above. You're combining information from all of the spectral lines, and because of that, it's easier to see weak signals. And also, any noise is averaged out over many different pixels. Okay. Which type of star will have the least radial velocity noise? So this is astrophysical noise that you don't like. And which one will have the least amount of this noise? A delta Scuti pulsator, a young spotted M-type star, an old slowly rotating sun-like star, or a young protostar that is flaring? Yes. So the star that will have the least amount of radial velocity noise or jitter is an old, slowly rotating sun-like star out of the ones that I've listed here. So the other answer that people answered was a young spotted M-type star. And so this is bad because, or those stars have lots of noise because they have star spots on them. And star spots mostly occur on young stars and mostly occur on spotted, or spotted means they have star spots on low mass or M-type stars. And that adds radial velocity jitter and noise. Okay. What do eclipsing binary systems allow us to measure? And sorry, this is another short one. These are the 3 questions that I added at the end, and I must have forgotten to move those. So both stars' masses, both stars' radii, the orbital period, or all of the above. Okay, good for the 2 people who answered it. Yeah, so eclipsing binaries. This should be the last one. That's only 20 seconds, and I'm sorry. Eclipsing binaries, you can measure both stars' radii because they're eclipsing. So we see the transits, and transits allow us to measure radii. And we can measure both stars' masses because we can get the radial velocity of both stars. And the orbital period you can actually get with both the transits and with the radial velocities. So you can measure all of the above. Okay. What can be determined by measuring the Rossiter-McLaughlin effect? Can you determine the inclination of the exoplanet's spin? Can you determine the inclination of the star's spin? Can you determine the alignment of the exoplanet and the star's spin axes? Or can you determine the alignment of the stellar spin to the exoplanet's orbit? So the first one is what's the inclination of the exoplanet spinning? The second one is what's the inclination of the star spinning? The next one is the alignment of the exoplanet and the star's spin. And the last one is the alignment of the star's spin and the exoplanet's orbit. Hopefully those make sense. Okay, great. Yeah, so from the Rossiter-McLaughlin effect, or by measuring the Rossiter-McLaughlin effect, we can determine the alignment of the star's spin and the exoplanet's orbit. Okay, and this is the last one. An exoplanet transits a star that is rotating with the following orientation. So there'll be a picture. Which radial velocity plot would you observe? So this one's harder, so I gave you more time so you can look at them more closely. Oh, great. Most of you got that. That's great. So because it's an aligned orbit, we see an equal amount of increase as decrease. Okay. Great, and everybody did a really nice job. So I will stop sharing now. And if you don't have any questions, I was hoping to finish up, since we didn't get to finish all of the workshop from yesterday, I was hoping to move to the workshop a bit early today so we would have time to do today's workshop and finish up yesterday's workshop. So I think to keep on schedule, can we take our break a bit early now?
Yes, Aurora. So there is no problem to take the break right now. It should be for 25 minutes, but I think it's a bit longer if you want to complete what you started yesterday and start the one from today, because I was checking on it and I'm really sad I won't be here to watch what you're going to do. So let's reconvene at 10 a.m. Colombian time, 4 p.m. your time, correct?
Yeah, that's fine.
Okay, perfect. You don't have more questions right now on the chat, so I'll guess that after the break, maybe there will be some questions. So yeah, I don't know. We invite all of you to participate to the chat. All the questions will be passed straight to Aurora, and she will be happy to answer all your questions. So see you in 18 minutes to complete the workshop from yesterday and to start the one from today.
Great.
Okay, bye.